Yes, please.
Well, so thanks for invitation to the conference. I am Zina Milodashvili, and I'm pleased to present the work titled Dependable and Resilient Emergency Multi-Attribute Group Decision-Making Approach for the Selection of Humanitarian Aid Distribution Centers. Nowadays, special attention is paid to the engineering of dependable and resilient intelligent systems and models. This direction includes also multi-attribute group decision-making models and systems in emergency environment. As a rule, this environment is characterized by insufficient objective data and lack of response time to solution of the problem. We consider in this direction the new multi-attribute group decision-making of facility locations selection problem FLSP based on the TOPSIS approach. TOPSIS stands for Technique for Order Preference by Similarity to Ideal Solution. Well, usually facility location selection problem models designed for extreme situations can be used during the delivery of humanitarian aid in the affected regions. For relative simplicity, we consider only one direction of these problems, namely selecting the location of humanitarian aid distribution centers in the case if we have the disasters like earthquakes, floods, terrorist attacks, or other disasters. Location planning for potential distribution centers is critical because of traffic congestion and, of course, other problems that arise from transportation facilities under extreme conditions. The increasing number of cargo shipments has a negative impact on the local population and the environment. Of course, the local municipal administrations use stable rules for cargo transportation, such as time, limiting delivery time, special delivery zones, special rules, and so on. So, with the introduction of these rules, logistic operators face difficulties, of course, when planning the location of service centers. Planning of location of service centers in a specific situation is a much more multifaceted problem that requires taking into account many attributes of an uncertain nature, such as the maximum scope of service to the customers, the minimum cost for service, the minimum impact on local residents and the environment, as well as the response to the rules of cargo shipment, and so on. Let us consider the fuzzy TOPSIS approach for selection index of a candidate humanitarian aid distribution centers. When we consider decision-making problems under conditions of incomplete information, we have conflicts between information uncertainty and inaccuracy. And in order to increase the accuracy and reliability of decision-making, along with objective data, we have to also to take into account subjective data from experts as well. Yes. In such a case, the correct selection of semantic forms of expert data becomes important. In this work, We focus on Q-rank orthopair fuzzy numbers. Suppose that we have locations of candidate humanitarian aid distribution centers. We denote it CS. This is the set of candidate sites, and these locations are known beforehand. And suppose all attributes which determine the selection of candidate sites is the set omega. These attributes may be as, for example, access by specific transport modes to the candidate site, security issues of the candidate site from malicious actions, and so on. Different costs, certain impact on location of location on the environment, and so on. Let us also suppose that these attributes have weights given by set W. And suppose that we have T experts, expert 1 up to expert T, invited for making some evaluations. And suppose that also that case expert evaluation of case expert with respect to the attribute omega j on the candidate side I is denoted by rank orthopair fuzzy number Xijk. For each expert, we provide binary fuzzy relation Xk. This is this set, as you see here, and this is a decision-making matrix with elements given in Q-rofts. Of course, if the attributes may differ from each other, one may be of cost type and the other may be benefit type. So here we use also conversion between them. The data from experts should be aggregated in echelon decision-making matrix, one matrix. And we are building the fuzzy topsis approach, which will allow aggregating objective and subjective data for every candidate site into numeric values. This is the selection index for candidate sites. Formally, the aggregation can be thought as the topsis relative closeness of the alternative on Xij. Here is the formula. Beta E, this is the index, and it is the value of topsis aggregation on this row of evaluations, candidate site evaluations. Let us consider the ranking scheme, how we should rank these candidate sites and choose the better optimal from them. Here are some steps. Step 1, selection of location attributes. It is connected with the selection of location attributes for assessing potential locations for candidate sites. As we take the key attributes such as post-disaster access by specific transport modes to the candidate site, post-disaster security of the candidate site from malicious actions, post-disaster connectivity of the location with different type of transportation, different costs of transport, resources, products, and so on, certain impact of the candidate site location on the environment, proximities of the candidate site from the central location. These are the key attributes. Selection of candidate sites location. It is connected with selection of locations for placement of distribution center. Using knowledge prior experience in certain aspects of the geographical area of the extreme events, the decision makers should identify locations for placing service centers. Of course, if the municipal administration has some restrictions on certain areas, they are taken from consideration, and this is okay. Some details. Preferably, potential locations should serve the interests of each city stakeholder, such as citizens, municipal administration, and so on. Step 3. Assigning CUROF ratings to attributes relative to candidate sites. Suppose that for each expert, there is a fuzzy binary relation given by matrix of ratings made by experts, and here Xijk is the rating of the candidate side, CSI against with respect to attribute omega j. Next, step 4. In this step, we should choose the common Q-rank for all assessments. This means to find positive integer number such that for each assessment, these inequalities should take place by formula 2. Step 5. Construction of an echelon CUROF decision-making matrix for candidate sites with respect to attributes. Assume that the experts' weight ratings are given. Each expert is evaluated itself, and these ratings are numbers, positive numbers, C, K, and their aggregated overall ratings is defined as the weighted sum of their ratings by a formula calculated by formula 3. So the matrix of the relationship constructed as a reference decision matrix has the form given in formula 4. This is. Of course, here also we calculate the values of function score and accuracy. These are calculated by components of Q-rank orthopair fuzzy numbers. These are the ratings, Xij. And step 6. Here we should identify the CUROF positive ideal solution and negative ideal solution. Here we choose the maximum values ratings in columns, and they have such a by such condition we can be chosen by these two conditions. Of course, in real life, these are infeasible alternatives: positive ideal solution and negative ideal solution. Step 7. We have to calculate proximities, distances between the alternative candidate site location and the CUROF positive ideal solution with CUROF negative ideal solution. So the distances are calculated by formulas 5. By formula 5. This is the CUROF in terms of CUROF operations, arithmetic operations. Step 8. Calculation of the relative closeness of Topsis aggregation as a candidate site selection index. Generally speaking, the bigger distance from candidate site to negative ideal solution, and the smaller the distance between this candidate site and positive ideal solution, then this alternative for the selection is better, of course. In the TOPSIS method, we introduce new or some modified formula for relative closeness, and this is the given by formula 6. Here, small and large are functions, and they may be chosen such that they should be strictly decreasing and or increasing fuzzy values on given interval in the segment 0, 1. And we, in our calculations, we choose such values. Step 8, ranking of candidate sites for the opening by their selection index. We said that candidate site CSI is more selective for the opening than candidate site CSJ, and write this relationship if and only if beta E is greater than beta J. So now let us see the work of this algorithm for numerical example. Here we demonstrate the situation with 5 humanitarian aid distribution center candidate. The number of candidate sites are 5. Suppose also that the attributes is also 5, for example, and we choose omega 1 is accessibility, omega 2 is security, omega 3 is connectivity to multimodal transport, omega 4 is costs, and distance to customers, proximities. Well, suppose that experts generated attribute weights based on the principle of consensus as attribute importance levels. Here are the given. Suppose that the experts have its weight ratings similar, for example, and so CK is 1 divided by 3. And also suppose that each expert has made ranking estimates for every candidate site E. And here these are evaluations and these ratings are given by these tables from expert 1, from expert 2, from expert 3 evaluations. And we should aggregate these in one table. The ratings of all 3 experts are aggregated in one table. We ran all above data on the new fuzzy TOPSIS algorithm, and we obtained the TOPSIS estimates for candidate center selection indices, which are the values of them are as given here. And so the candidate sites are ranked in this way, and of course it is obvious that the best candidate how we can choose is in this order. Candidate CS second candidate site, then 5th, then 4th, then 1st, and then 3rd. Well, in this work, so we can say that new fuzzy model of object placement is developed in extreme environment under uncertain conditions. Experts evaluate each candidate humanitarian aid distribution center with respect to uncertain attributes. And TOPSIS method is developed for the formation and representation of expert knowledge on the planning parameters of emergency service facilities. In this approach, we propose a score function-based comparison method to identify the curve positive ideal solution and negative ideal solution. And for illustration of this, everything of this, we consider a numerical example. From the practical perspective, the more detailed constraints and maybe more complex constraints to the problem are supposed to be developed in our future research, and use also different other semantic forms for these problems. Thank you for your attention.
Thanks. Are there some questions? Dear colleagues, are there questions? And Professor Medodashvili, thank you very much for your presentation.